the lead developers of Sundials. I'm not the person in charge of the project. That's Carol Woodward, but she's out of the country right now, so I'm going to fill in. We've heard a little bit about Sundials already during Barry's talk, and there's a lot of similarity between the way that we think about problems and the way that PEDC thinks about problems, and so I'll try to just highlight those similarities without going into all the details and all those specifics. So Sundials stands for the suite of nonlinear and differential algebraic equation solvers. And specifically, we focus on time integration and nonlinear solvers in particular. And so by time integration, I mean systems of ordinary differential equations or differential algebraic equations. We can also incorporate forward and adjoint sensitivity analysis, which I'll talk about more in a little bit. Similarly, we have Newton and fixed point nonlinear solvers. So if you're doing a non-time dependent problem, how might you go about solving those nonlinear systems? It's written in C, like most of the other packages that you've heard about so far today in fast math, though we have Fortran interfaces as well for those of you who use that in your applications. One of the things that we think about and as part of our big design philosophy for Sundials, as opposed to some of these other packages, is we really want it to make it very easy for you to incorporate our solvers into your code. So you don't have to rewrite your data structures, you don't have to redo how you focus on your problem, you just teach us how to use your data, and we'll be able to do almost all of our stuff. And the idea behind that is very similar to what Barry talked about with PEDC, is there's these vectors that we can code to, but under the hood, the data structures are essentially are independent of those vector operations. So I'll talk more about that a little bit later too. Moreover, we have a pretty modular implementation. You can swap out different components. So although we provide linear solvers, some simple preconditioners, not as nice as some of the ones we've heard about so far today, and different kinds of vector structures, you can supply different ones that might be tuned to your application. So if you have a very nice preconditioner for your, I don't know, some crazy problem, you can plug that in as opposed to trying to use one of them that we supply. And as with all of these, it's open source and freely available. So also, like a lot of all the applications you've heard about today, Sundials is used all over the place. It's used for researchers in universities and in industry, all kinds of stuff. I've worked on a few of these problems. I'm not going to go into details here. Okay, so the main thing I want to do is kind of talk about the different solvers that comprise Sundials. It's a suite of different solvers, and you can use one or another, or you can combine them together. And so I'm going to start with the one that's the workhorse, the one that most people know and that they use more often than any other of these. Okay, so the big one that we have is called CVODE, and it solves systems of initial value problems. And so in the simplest form, we can write down an ODE, a system of ODEs, as y dot is equal to f of ty. Okay, so y is our vector of functions that define our unknowns, and t is our independent variable. We can think about it as time, and we have some initial condition for what our state is at some initial time. And so CVODE uses these things called linear multi-step methods. It changes the order of accuracy of the method and the time step size adaptively to squeeze as much efficiency out as possible. Okay, and so the idea, for those of you who are not numerical analysts, is that what a linear multi-step method tries to do is it takes this equation up here and it approximates it using a linear combination of y at different time steps. So yn is the current time step, yn minus 1 is the previous time step, etc. Some linear combination of those, a linear combination of the right-hand side f evaluated at the current time and old times. And through using this linear combination, these linear combinations to approximate this ODE system, we can try to approximate the overall solution to the continuous time equation using discrete time steps. So there's two basic solvers inside of CVODE. The first class of them are called Adams-Moulton methods. Those are great for non-stiff problems. The second class of them that we use are called BDF, or backwards differentiation formulas, and those are really good for stiff problems. So when you use CVODE, you can pick which one of these you want to try out for your problem. I want to try out the Adams method, or I want to try out the BDF method as you go. Since no linear multi-step method is provably astable when they have an order greater than 2, we have stability limit detection to try to help figure out if the problem is going unstable and to limit the time step size when you're using an order higher than 2. So you can have up to 12th order for Adams here, or up to 5th order for the BDF. Both of these result in a nonlinear system of equations. So like Barry said, time integration often relies on a nonlinear solver to help figure out what each time step is. So for solving each time step, we're going to use a predictor-corrector scheme. The predictor is given by an explicit method, and so this is just a linear combination of old stuff. Notice yn is the thing we're looking for, and here the summation goes from yn minus 1 and fn minus 1. And so we're going to use old data to get a prediction. That prediction isn't going to be the answer to this nonlinear system of equations, but it's a good guess. And then we're going to correct that prediction using one of a variety of different nonlinear solvers. So we can use a fixed point-based solver or a Newton solver. And I'll talk more about those nonlinear solvers a little bit later. Is that all right with everybody? Any questions? Okay. So what makes CVODE, yeah, go ahead.
So are these predictor-corrector methods all second order in time, or are they higher order as well?
They're up to the order of the method. So you can use the 12th order Adams method, and it'll do a 12th order explicit predictor with a tiny, tiny, tiny stability region, and then it'll try to, and then the corrector will be the solution to the Adams-Moulton thing. So the reason we think about CVODE as a solver as opposed to just a time stepper. Any of us can open up a numerical methods book and implement something we find on page 75. But what makes it a solver is that you specify how accurate you want your solution, not how big you want your time step size to be. If you need 3 digits of accuracy because you're going to solve some engineering application, we're going to try to take the biggest time steps we can and get you the solution as fast as possible, but that gives you those 3 digits of accuracy you're asking for. So the basic idea is for all of your solution components, you're going to have a bunch of them. You're going to specify an absolute tolerance, what's a small number for each component, and then what's the relative tolerance for the whole system, specifically how many digits of accuracy do you really want. We use those to construct a weight vector we call EWT, and not to go through the details, but with this error weight vector that incorporates your tolerances, we can use that to measure error in all of the iterative nonlinear solvers, linear solvers, and everything inside of CVODE and all of SUNDIALS solvers to try to ensure that we give you an answer that's just accurate enough without overdoing it and nailing down digits that you don't care about. And so then the idea is we want to make that time step size as large as possible so that your error is small enough. And so in this weighted root mean square norm defined using this error weight vector, a norm that's smaller than 1 means it's within your tolerances. And so we specifically in CVODE try to make sure that the corrector and the predictor differ with a norm less than 1/6, which would say that these 2 different approximations to the answer agree pretty well. Okay? So in CVODE, it adapts the time step size and the order of accuracy. And so it's not just going to take a big time step size or a small time step size, but it's also going to change between a second order accurate method to a third order accurate method to a fifth order accurate method in order to try to get the biggest time step it can. And the basic heuristic behind doing that is it tries to figure out what the biggest time step size it can take at your current order. So if Q is your current order of accuracy, then it's going to estimate what's the local temporal error in your problem, and it's going to ask if that error is less than 1. If it's less than 1, then it says, okay, it was a good enough time step. Let me pick the next time step to take. If there was too much error, it makes the time step size smaller and tries to recompute the step because it doesn't want to give you a bad answer. It's going to redo the work to give you a good answer. It'll use this approximation to figure out what the optimal time step size delta t prime is for the next time step. And then it'll figure out what would that be at the current order of accuracy Q. It does the same thing for an order of accuracy lower and an order of accuracy higher, and it picks the order of accuracy and the time step size to get you as close as possible to the end. What's the biggest time step size it could take? Yeah?
Can you restrict it or set a minimum order?
Absolutely. You can you can't set a minimum order because linear multi-step methods have to start with first order because they have to bootstrap up. But you can set a maximum order, and you can set minimum maximum time step sizes. You can control a lot of those kinds of things. Okay, so that's all I'm going to talk about for CVODE. The other solvers are similar, so I want to go into more detail in that. So the solver that I'm actually in charge of is a solver called ARKode. It also solves systems of initial value problems, though they're written in a slightly more general form. And so up here, again, we still have a y dot, so the dy dt, and an f on the right-hand side. But now f has been split apart into 2 components. So instead of f containing all of the physics in your problem, you can write it as the sum of an explicit portion of your physics and an implicit portion of your physics. Barry talked about how you could have stiff and non-stiff components in a problem and write your ODEs so that your solver can keep track of the stiff and non-stiff stuff. So this is a way to do that as well. The stiff parts go into FI, the non-stiff go into FE. And similarly, when you have a a finite element-based calculation, you might have a mass matrix over here on the left. Okay, so this is a more general way to write down systems of ODEs. And so the types of solvers we use inside of ARKode are more similar to the types of time integrators that are inside of PETSI. We're going to use variable step size, not variable order, additive Runge-Kutta methods. So what additive Runge-Kutta methods do is they combine an explicit method and an implicit method, a proper selection of these two kinds of methods so they're compatible and they work together, with the idea that through these equations, which we don't have to stare at too long, we're going to be able to think about the explicit parts explicitly. If you'll notice, this summation goes up to I minus 1. The implicit parts with the Fi are going to be treated implicitly. This sum goes up to I. And so in solving for each stage, Zi, we're going to have explicit physics, which we don't have to incorporate in the nonlinear solver, and of course implicit physics that we do have to incorporate in the nonlinear solver. We solve each of these nonlinear equations, and when we're done, we can glue together our solution yn for the time step and this thing called the embedding, this embedded solution yn tilde. And of course, in solving these nonlinear problems, we can use Newton methods, fixed point iterations, things like that. So like CVODE, we're going to estimate our error. We're going to estimate our error as the difference between the solution and the embedding, as opposed to the difference between an explicit predictor and an implicit corrector, and that'll have a bearing, a nice effect a little bit later. We don't adapt the order of accuracy between time steps, but you can pick what order of accuracy you want to use. So you'll run the whole thing with a fifth order accurate method or the whole thing with a second order accurate method, whichever one you want to do. But we will try to maximize those time step sizes to get you to the solution as fast as possible. These ARKode, since it's based on multi-stage Runge-Kutta methods as opposed to multi-step, linear multi-step methods, there's two big benefits and one big detractor. So one of the big benefits is we can get high order accuracy and we don't need the long history. We don't have to start out with a first order method and then go to a second order method and then go to a third order method, because linear multi-step methods need to know what the solution looked like in the past. Multi-stage methods don't, and so you can have a fifth order accurate method from the very first time step. And what that really allows you to do is do spatial adaptivity. So as Lori talked about this morning, if you're adapting your mesh to zoom in around a region that's really interesting, and you have much more refinement in one spot, if you needed to do a linear multi-step method, you'd have to project those solutions throughout all of your history that you're keeping track of so you can have a high order accurate time step. But with a multi-stage, all we need to know is the current snapshot of your adapted mesh, and then we'll take a time step that's whatever order of accuracy you wanted. And so we can get high order accuracy without having to jump through a bunch of hoops. Moreover, both the solution and the embedding can both be astable, or stable for all time step sizes. And so instead of comparing an explicit and an implicit solution for your error estimate, we're comparing two implicit solutions. So for stiff problems, it's a much better estimate of the error than we have for the linear multi-step approaches. The real problem, though, is unlike CVODE, where we have one nonlinear solve per time step, we're now going to have multiple nonlinear solves per time step. So while we get some benefits, we have to work a little harder. And so, of course, on some problems, CVODE's just going to beat ARKode out of the hands down. But in other kinds of applications, we can use ARKode, and it'll do a lot better than CVODE can. The last thing I want to mention about ARKode is that I built it to look almost just like CVODE. So if you've already set up your application to use CVODE with only very minor changes, usually just search and replace for CV into ARK, you can then run ARKode, a simple interface for that as well. And of course, that allows you to try out the different algorithms in a real simple way. Moving on past initial value problems, we can think about differential algebraic equations. And so the most general form for a DAE is writing it implicitly. So some function of the time, the current solution, and the dy dt has to be equal to 0. However you want to write it down, any initial value problem can be written in this form. And of course, you give your initial condition. So typically, if the Jacobian of f with respect to y dot is invertible, then you'd convert this into a system of initial value problems, and you just use CVODE, or you use ARKode instead. But for a lot of applications, that's not a very good approach. And so you might want to try to solve this kind of problem directly. And so if you're trying to solve this formulation directly, it's what's called a differential algebraic equation. And there's a differentiation index, et cetera, that we can define for these kinds of problems. So IDA is the sundial solver that's used for DAEs. And so we solve the generic form of the DAE. It also uses BDF methods like CVODE does. It doesn't use the atoms approach, so you have to have the stiff solver, the stiff linear multi-step solver. It's a C rewrite of a code called DAS-PK, which is a Fortran code, and that code's been around for a long time and people love it. So this is a C version, essentially, of that same code, written by some of the same authors. It's best used for implicit ODEs and index 1 DAEs and Hessenberg index 2 DAEs. And if you don't know what I'm talking about there and you have a DAE, come talk to me and we can figure out how to convert your problem into one of those kinds of problems so you could use IDA. A challenge with DAEs is to get a consistent set of initial conditions because you need a y and a y dot such that at t naught f actually equals 0. Once you discretize things, it often doesn't. And so there's a nice solve inside of here to help you get initial conditions that'll work correctly. All the nonlinear solves are based on Newton's method. And one of the cool things that IDA has that the previous solvers do not are that you can specify constraints. So if you have solution components that just cannot be, they have to be strictly positive, like a density, for example, or a temperature, or has to be strictly negative. Can't think of a physical intuition for that, but let's just pretend there is one. Or a non-negative or a non-positive values in your solution. You can tell IDA you want those, and it will do its best to make sure that you don't deviate from those values on your solution, those bounds. So CVODE and IDA have these sensitivity-enabled versions of the solvers. Notice there's an S at the end of both of these, CVODE S and IDA S. These stand for the sensitivity-enabled components. There's not an ARKode S, at least not yet. And so the idea is these allow us to do what's called sensitivity analysis. And so sensitivity analysis, just the simplest way to think about it, is if you have outputs from your model, and those outputs somehow depend on parameters that were inputs to your model, but you want to know how sensitive are those outputs to those inputs. What are the partial derivatives of the outputs with respect to perturbations of the inputs? That's sensitivity. How sensitive are the outputs to the inputs to these problems? And it turns out that in scientific computing right now, and increasingly throughout the last 5 to 10 years, sensitivity analysis has become a much bigger area. People at first were just trying to do forward problems. How do I just simulate this thing? But after you can simulate it, you want to know whether that parameter was important or not, or what's a better model. And so people are increasingly using sensitivity analysis in scientific computing in different kinds of problems they're looking at. And so there's a lot of applications that we list here that you could use these kinds of things for. There's 2 basic approaches we use for sensitivity analysis in CVODES and IDAS. First is forward sensitivity analysis, and the second is adjoint sensitivity analysis. The basic way to think about it is with forward sensitivity analysis, if you know how the outputs for one time step depend on changes to those parameters, you can specify those equations, those forward sensitivity equations, and we'll integrate those in time along with the solution. So at the end of the day, you know how sensitive the final outputs were to those parameters. Maybe you don't know those partial derivatives of how your outputs for each time step depended on the parameters for the inputs. But so we can try to do the adjoint sensitivity analysis kind of solve instead. And the idea there is we're going to do 2 forward solves and 1 backward in time solve. And so what you have to provide is some mechanism for us to be able to integrate backwards in time, which is this adjoint problem. And so we can use either of these 2. The adjoint sensitivity analysis is more costly than forward sensitivity analysis, but they're both rather useful in standard practice in the applied math community. But when doing adjoint sensitivity analysis, a real challenge is how do you do the backward simulation in an efficient manner so you get all these things. And we use a process called checkpointing, which is rather standard in these adjoint-based simulations. So the last solver that's part of SUNDIALS is called KinSol. It's a C rewrite of the Fortran code NKSol by Brown and Sod. That was the very first PDE-based Newton-Krylov solver in existence. These are the guys who invented this stuff. And so that solver was translated from Fortran into C, and it's had upgrades over the years, and that's what KinSol is now. So it has a long history as a code. The Kin stands for Krylov inexact Newton. Sol stands for solve. So, of course, it's based on Newton solvers, like a lot of the codes you've heard about so far. And the basic idea behind Newton's methods, if you're not as familiar with them, we're going to take a guess and get our new guess as the old guess plus some update S. And the difference between different kinds of Newton methods are how they get the update vector S. Okay, and so inexact Newton methods or modified Newton methods are the 2 basic ones inside of KinSol. And so an inexact Newton method solves this linear system. J is the Jacobian of f with respect to u. S is the solution vector we're looking for, and minus f, where f is this nonlinear problem we're trying to solve. But instead of solving this linear system exactly, it'll solve it approximately using Krylov methods, GMRes, something like that. Modified Newton methods solve the same linear system, almost, except they use an old version of the Jacobian, something they computed a while back and they've been reusing to try to get squeeze out some benefit. But they're going to directly solve this. So they're going to have a really accurate solution to this linear system as opposed to just a very inaccurate one. Kinsol also allows us to specify constraints on the solution vector. Moreover, we can scale the equations and unknowns separately. If you know the units in your problem are kind of nasty, you can normalize the equations and you can normalize the unknowns in order to make the floating point arithmetic a lot happier. For nonlinear problems that are really hard to solve, we can have backtracking line search to help increase robustness. And if you're using an inexact Newton method, there's been research over the years on how best to determine when how approximately you actually want to solve this problem. Do you want to solve it really poorly or really well? And so that comes into this forcing parameter A to K. And so there's all kinds of research into the right A to Ks. And so we have different things you can use in there. So there's some new additions to Kinsol and in turn to some of the other solvers inside of Sundials. And instead of just using Newton methods, we also have fixed point solvers and accelerated fixed point solvers and Picard fixed point solvers. So just the basic idea about what a fixed point iteration is. Let's say we wanted to solve f of u is equal to 0, this nonlinear problem that we have here. Well, an equivalent problem is to solve u is equal to g of u. So this is a fixed point problem. And it's in every way equivalent to a root finding problem as long as you define g and f compatibly. And so the fixed point iteration says your new guess is just g at your old guess. So obviously if this converges, this is something you converge to, this is the same thing you converge to, u is equal to g of u, and you've solved the fixed point problem. The basic fixed point iteration defines g in this way. So if f is 0, then that disappears and g of u is equal to u, right? So it's the same thing as the nonlinear problem. A Picard fixed point iteration defines g in a slightly different way. It's going to split f into linear and nonlinear portions, and it's going to define g as this L inverse n, or equivalently u minus L inverse f. Not that you need to pay attention to the derivation, but at the end of the day, the new guess is the old guess minus L inverse f, which is the same thing as what Newton's method did. The new thing is the old thing minus, there's a minus sign here, j inverse f. Right? And so it's essentially the same basic thing, except that instead of using J, it'll be using this other matrix L that it'll reuse throughout the entire solve. So what's nice about fixed point iterations is that if G is a contraction, which mathematically just means this thing here, then you can prove that fixed point iterations will always converge. Always. They're just going to be slow. Okay? And so they're going to converge at a linear rate. It might take forever, but you know that you're going to get there, like the tortoise and the hare. Now, you can accelerate those, and Newton's method is actually just a fixed point iteration that has a really nice g. Okay? And so that's going to be faster. Or you can use other kinds of acceleration strategies, and so we use this thing called Anderson acceleration that I haven't talked about here, but it's essentially a way to accelerate this basic fixed point iteration. Okay, so just 5 more minutes. I'm going to talk about the general idea behind how Sundials is structured. It's very similar to how PETSI was, so I'm going to kind of skip the parts where we're similar so that we can, now that you know what the solvers there are, then I can talk about the hands-on problem you guys will look at later. So the Sundials vector module is generic, a lot like the PETSI one. We code all the solvers to a generic interface, and then of course you can, so the way I think about it is like an object-oriented approach. There's an abstract base class. Of course, this is in C, so we don't actually have these things, but we have an abstract base class that just says what a vector is. It has data, there's a content, and there's operations that are defined on this data, exactly like what Barry said. We code almost all of our solvers. The direct linear solvers can't do this, but all the other solvers, time integration, everything, just uses these basic vector operations. And then, of course, when you actually want to do a real problem, you need to actually tell us what your vectors look like. And so you can think about that as the derived class from your abstract base class. And so so there's, in that case, you'd say what actual stuff is in the vector, what are the actual ways you operate on the data, and you need to give us some utility for making copies so we can make temporary vectors for our solvers. So we provide 4 vector kernels, a serial one, two threaded ones, and an MPI-based parallel implementation. In all of these, vectors are logically 1D arrays in memory. You say how big they are, local, global, like in PETSI. Because they're unit stride, these 1D arrays, then the operations are really efficient. What I really like from these is not only can you use them, but I do a lot of other problems that we can't just use one of these basic data structures. And so I just use these as templates for building a data structure that works really well for a very specific different problem that has ghost zones or all kinds of other stuff. And so they're really good for you to just build your own thing off of, your own derived class off of that abstract base class, so you can use all the SUNDIALS solvers. Okay, lots of linear solvers. There's not too much to say here. Just like PETSI, we have Krylov methods, dense direct methods. We have sparse direct methods. We didn't implement ourselves. We actually call Sherry's SuperLU MT package for that, or KLU. So yeah, there are different kinds of linear solvers. When you use linear solvers, you need to have a good preconditioner. Well, when you use Krylov methods, you need to have a good preconditioner. And so just some ideas with preconditioning is you want the preconditioner to really do a good job approximating the Newton matrix, but you don't want it to do too good of a job. You want it to be really efficient to construct and solve. And so there's different approaches for that as well. The big thing we have here is we don't give you a lot of preconditioners ourselves, but we make it really easy for you to hook into other stuff. So I regularly call SuperLU, Diff, and Hyper inside of my applications from SUNDIALS in hooking up to their linear solvers. So there's root finding if you need it. I'm not going to go into details on that. And there's Fortran interfaces as well, which I mentioned earlier. So the basic idea behind how SUNDIALS codes work is very similar to how all these other codes work. You're going to include some header files that say, what solvers you want to use, what vectors you want to use, et cetera. Inside your main routine or whatever function it is, you're going to create a data structure for the solution vector. Make a vector that's going to hold your answer. Then you're going to create your solver. Say which solver you want. You then initialize it, and you hand us that vector, and we make copies of that because we're going to need temporaries. Then we're going to set a bunch of default solver parameters like the time step sizes and things like that, and you can change them, change all the parameters you feel like. If you need a linear solver, you do the same stuff there. After you've set everything up, you can call the solver once. You can call it 100 million times. However much you'd like, we allow you to reuse it. There's no weird destroying things and needing to delete and reallocate. And then when you're all done, you just destroy it, and then that way you can clear out your memory. So it's available open source online. You can look here. So with that, I'd be happy to answer any questions you have.
So for CVODES and ARKode, does the user need to provide the Jacobian for the system, or the system will using numerical differentiation to get the Jacobian?
So at the simplest level, if you want to use, this is a parallel conference. So if you're going to be using a Krylov solver for either CVODE or ARKode, and for ARKode, let's assume you don't have a mass matrix, it's just the y dot. Then you can provide a Jacobian vector product. We don't ever want the Jacobian there. We just want how do you do a matrix vector product, and you would compose that routine yourself, or you can ask us to do a finite difference approximation for you. It's relatively efficient because we only need the matrix vector product, not an actual matrix. We never fill in a matrix of data for these Krylov solvers, and so they're actually rather quick. Now, of course, if you're doing that and you want it to be scalable, you need a preconditioner, and that's where you're going to want to come up with Jacobian entries and use Hyper or something like that for a real scalable multi-grid type solver.